Welcome back to ECE 320A. We have a week left of lectures. Today, Thursday, and next Tuesday. Today we'll finish up filters. Thursday we'll get into three-phase power, sort of a very quick, I'm not sure, so stay tuned. And then in a week, I believe we said we were going to have a review. There is a homework assignment. Number 6 is now available to you, and that's due Saturday the 7th. And here are the different modules in D2L if you want additional information or if it's needed. And I think I might actually refer to one of those, but these are now smaller packages of the material in terms of they're not each one does not represent 75 minutes of material. What I want to do today, fairly busy, is go through active filters and basically just show you what some of those structures look like for the low pass, high pass, band pass, and band reject. And then we'll get into scaling. How do we frequency scale? How do we magnitude scale? Typically you will design a filter on a normalized transfer function or on a normalized filter. How do you convert that to be something different? That's what we use scaling for. And then I will simply quickly remind us of what we were talking about a week ago in terms of we can't simply combine a first order stage and expect the cutoff frequency to remain where it is for each of the poles. And for that reason, we need to become a little bit more, what do I want to say, strategic in where we place our poles. They can all be a distance of 1 from the origin. If we want a normalized frequency of 1 radian per second, the poles will be 1 radian per second away in terms of their distance. But now where are they located on that unit circle away from the origin? And that's where the Butterworth pole pattern comes into play, and I'll try to give you a way to think about how these different numbers of poles distribute themselves on that unit circle. Why do they appear in the locations that they do? Obviously, if we have a first order filter, it's going to be at s equal -1. Once we get higher, when we have a second order filter, we're not going to locate both of those poles on top of each other at -1. That will sacrifice our cutoff frequency. It will be lower than what we were hoping. We want to keep that cutoff frequency at 1 radian per second. And we'll show how we can put pieces together and still maintain that cutoff frequency at the same location. And obviously then all of our designs are not going to have a bandwidth of 1 radian per second. That's why we need what we're going to talk about now, which is scaling. How do we scale that? So if I now want a 100 hertz low pass filter, how do I realize that with the circuit elements that I have in hand or that I have available to me? That's where we are going. So let's quickly scroll through some pictures relative to how can you realize, if I now said give me a passive low pass filter, first order, you should be able to just sketch the RC circuit. Here is a similar first order low pass filter, but now this is active. It has an op amp, and this is figure 15.1 in the textbook, and you should be able to derive the transfer function by simply saying, oh, I have a feedback impedance, which is the parallel combination of R sub 2 and C, and I have an input impedance given by Z sub 1, and now you know what that transfer function is between V sub I and V sub O relative to the feedback impedance, which is what I'm saying is right here, you could say, oh, this is Z sub F, and this is Z sub I. And then you could show by using KCL, let's say, at V sub N, was that Z sub 1 or Z sub I? Z sub I, do you remember that? Now you simply replace Z sub F and Z sub I with these complex expressions determined by how you've located those in this diagram. That's the low pass. It's dual, a high pass. You can see now that we're doing something a little different. We've now put our energy storage device, our capacitor, in the input impedance side of that op amp. We now just have a feedback resistor, and you could again use the Z sub F over Z sub I and determine what the transfer function is for that high pass filter. Again, I would just say let's focus right now on sort of understanding or appreciating these pictures and not really trying to frantically copy everything that's there. It's in the book. But here is how you could realize a bandpass filter. Now we are cascading these sections. We have a low pass filter right here. So that's low pass. And you throw all of this away. Then you high pass filter what's remaining, and that you could say looks here. So now you throw this away and you're left with what's in between. That's now your band pass filter realized as a collection, a strategic collection of a high pass and a low pass filter. And they then can be scaled by that inverting amplifier if we want to change the gain in some way on the output side. That's how you could build a bandpass filter. Contrast that with how you might create a band reject filter. Now we're not cascading them. These are in parallel. They're now summing these signals. So we have a low pass and a high pass. And what happens here? What color was I doing before? Let's see. This is now our high pass. So now we're throwing this away. And then our low pass, we're throwing what's to the right of the red, and the intersection of those is what's now really being rejected, because we're adding those two in parallel together. It's the sum of those. It's not the cascade combination of those filters. So in this case, this is what we are looking for. That's now rejecting that particular frequency band by the choice of the high pass and low pass filters cutoff frequencies. And that's how you could then build a band reject. Again, all of these were using active filters or op amps to produce those filter properties. Let's now look at how we might answer the following question. As I said in the intro, you probably aren't going to always be having the ability to design a filter that has a cutoff frequency of 1 radian per second. How do we change that? And maybe Josie doesn't have the exact parts that you need for the design that you created, and she now hands you some capacitors and says, here's your capacitors, good luck. And you now have to make sure that those capacitors work with your filter that you want to design. Or how can we obtain the pass band we want while still using component values that we have available? So now we maybe are restricted to using 10 microfarad capacitors. And we want to now figure out how do we make that happen. Well, we can do that by frequency scaling and by magnitude scaling. The frequency scaling gives us the passband that we want. The magnitude scaling allows us to use the components that we have available. Obviously, some are going to say, oh, I need these resistors specifically based on you requiring me to have these capacitors. So let's go through the idea of frequency scaling, which we are going to use a parameter k sub f, and magnitude scaling, which we will use k sub m. These are now numbers, and based on what we determine those numbers need to be, that will turn the crank, and now we'll say, oh, this capacitor needs to be this value. Oh, this capacitor needs to be that value. If we started out with some normalized fourth order filter, for example. Here's magnitude scaling, and my notation hopefully will be consistent. The initial value, or what we originally start with, that's what I'm subscripting with a 1. And the subsequent value, or the final value, will be subscript number 2. And now I want to magnitude scale, which now says I want my final impedance, Z sub 2, to be related to my initial impedance by this scaling parameter, this magnitude scaling amount, k sub m. And I'm restricting k sub m to be positive. How does that work for our three different circuit elements: resistors, inductors, and capacitors? We know what they look like in terms of their impedance. Z sub r, not a function of frequency, but it does have a value. It does have a magnitude. We want the original value to be scaled by some amount, k sub m, to produce Z sub 2. So now we simply plug in the appropriate expressions for Z sub 2 and Z sub 1. Z sub 2 is just R sub 2. We have K sub m, and then Z sub 1 is just R sub 1. If we need to magnitude scale resistors, then we simply scale them by the magnitude scaling amount, K sub m, that we've determined we need. And we'll maybe work through a little of this, and if we don't have time, you can find it in one of the small modules or lectures in the filter module. And I'll try to point you to that. Z sub 2. The impedance of an inductor is j omega L. We're not changing the frequency in this magnitude scaling. This is now j omega L sub 2. That's Z sub 2. K sub m is simply K sub m. And Z sub 1, that's j omega L sub 1. We can cancel common factors on either side, and this now is fairly clean. It says, oh, if we want to magnitude scale inductors, they scale like resistors. We now just scale the original inductor value by the magnitude scaling factor, K sub m. Capacitors, because of this reciprocal behavior of their impedance, it's going to be a little different. Z sub 2 is now 1 over j omega C sub 2. That's Z sub 2. Then that's equal to K sub m times Z sub 1, which is 1 over j omega C sub 1. Again, we can cancel a couple of terms that are in the same location on either side of the equality sign without changing anything. And if we solve for C sub 2, do you see that we could actually put this K sub m in the same location if we put it underneath C sub 1 on the right-hand side. Or in fact, if we now need to magnitude scale the capacitor, the final value of the capacitor is going to be C1 over K sub M. That's how we can magnitude scale capacitors. We also want to be able to frequency scale. We want to move that passband off of the normalized value of 1 radian per second. And in this case, we want the impedance at the final frequency to be the same as the impedance at the initial frequency. And we'll relate these frequencies by this scaling factor of frequency, K sub f. So our final frequency, omega sub 2, that we want to achieve, let's say that's our new passband, maybe that's 2,000 radians per second. We now need to find what K sub f needs to be to make 1 turn into 2,000 radians per second. You know the drill. So now we look at what happens with a resistor. We now want Z sub 2 to equal Z sub 1. And what is Z sub 2 for a resistor? This is really difficult. So now we have Z sub 2 as R sub 2, and that now is going to be equal to Z sub 1. And what's Z sub 1 when we have a resistor for our impedance? That's just R1. So if we're frequency scaling, we don't need to worry about adjusting the resistor values. They just go through unchanged. If we magnitude scale, we do have to accommodate those changes. What about inductors? Z sub 2. Now we have J omega sub 2 L sub 2, and we want omega sub 2 to actually be related to omega 1, so we can replace omega sub 2 by K sub f omega sub 1 in this expression. We know that we want J. This is now K sub f omega 1 L sub 2. But we want that to equal Z sub 1. And Z sub 1 is J omega 1 L1. And now we have some common terms on either side. And this now allows us to solve for, by comparing this with whatever is left over here, which is just L sub 1, we now can say that L sub 2 is found from the original inductor by dividing by the frequency scaling parameter K sub f. And that's different than when we magnitude scaled the inductors. And getting ahead of myself. Let's do the capacitor next. Here's C. We can do the same strategy. It's 1 over J omega C, and Z sub 2 now involves omega 2 and C2. Now we replace omega sub 2 with K sub f omega 1, and we want that to equal Z sub 1, which is 1 over J omega 1 C1. We can cancel the J's, we can cancel the omega 1's, and now we can see that K sub f C2 is equal to C1 to make Z2 equal Z1, or the final value of our capacitor when we simply frequency scale is now C1 divided by K sub f. What's nice is we can actually combine those. We can combine the magnitude scaling and the frequency scaling to obtain our ultimate final values. For the resistor, we just have to worry about the magnitude scaling. For the other two, we have to worry about frequency scaling and magnitude scaling, but once we have those values, we simply use these formulas to find the final values. What if somebody now gave you a transfer function, an h of s, and they said, oh, it has a bandwidth of 1 radian per second. I want it to have a bandwidth of 5 radians per second. How do I scale that so that I convert that normalized filter or transfer function's critical frequency to a new value? We do it similarly to how we did frequencies. S's are just frequencies. We now say, oh, we want omega sub 2 to equal k sub f omega 1. Well, S2 and S1 are j omega in terms of their relationship, so the S's scale just like the omegas. If we want to know how do I scale from an initial frequency to a final frequency, then we have S2 is equal to k sub f S1, which means that when we are scaling frequencies, we actually will replace S1 in our original with what we want it to be, S2. We won't be subscripting these S's because we just want an S in our original and final, so we just kind of have to keep track of which transfer function is the final and which one is the original, typically the normalized transfer function. So here's how does frequency scale a normalized transfer function. We now have h sub 2 on the left, h sub 1 on the right, and in h sub 1 we replace s sub 1, the original s, with s sub 2 over k sub f, as we had said up above. So here's an example. Now if in an interview somebody says, oh, give me a transfer function that's low pass and has a bandwidth of 1 radian per second. You now can immediately write down this 1 over s plus 1 and say, here's a normalized transfer function. Now they say, oh, on second thought, can you give me a transfer function that has a bandwidth of 5 radians per second? Now you go, I know how to give you this one. Well, now you could say, oh, that's right, I remember, I can frequency scale. You could just pull it out of the hat and say, here is a transfer function. If it's first order, it's fairly straightforward to achieve. But let's say that we now do that for this example, and we say, let's just try our frequency scaling idea or the concept. We now want, or this h1 of s is a normalized transfer function. It has a pole at s equal to minus 1, and its cutoff frequency then is at 1 radian per second. That's if you now drew the Bode plot. Does everybody now, when you see that transfer function, do you see the Bode plot? I see a Bode plot. What's its DC gain? Couple of answers could be correct. What's the DC gain of that transfer function? I'm not very good at hearing. You'll have to be louder. 1. One answer? I said there could be 2. No. 1 is okay. That's the absolute DC. You could also have told me it in dB. You could say, oh, the gain is 0 dB. That would be another for that particular frequency. Or, I'm sorry, for that particular transfer function. So you know it's DC gain, and You know where its pole is. You know now that's the break frequency, and after that the magnitude is sloping how much? How fast is the magnitude response rolling off? Minus 20 dB per decade, or minus 6 dB per octave. Again, two answers, depending on how you want to express the slope. It's the same slope or equivalent. So now let's say we want a break frequency, a pole at 5. Well, using what we said before, we want K sub f to be, that now relates omega 2 with omega 1. Omega 2 we want to be 5. Omega 1 was our normalized value of 1. We now want K sub f to be 5. That's our frequency scaling value. S new, which is S sub 2, is a scaled version of S old, or K sub f S1, and that means then that the old frequency in our normalized transfer function, S old, needs to be S new over K sub f. So we replace S in our normalized filter with S over K sub f to produce H sub 2. So now we're looking at H sub 1, and now we say, oh, this is S over K sub f. And do you see how I've just neglected subscripting the S's? Because we usually don't subscript our S's, but now H of S, or H sub 2, is associated with the new frequency, S sub 2, and H sub 1 is associated with the new the old frequency, which we're scaling by K sub f. If that's the case, then everywhere we had an S in the original transfer function, we replace it with S over K sub f. In our case, we had 1 over S, so that now gets replaced here, plus 1. And our K sub f we just found was 5. We can multiply by 1, which is 5 over 5, and now we have a transfer function, H sub 2, that has a bandwidth of 5 radians per second. And what's the gain? What's the DC gain of that transfer function? It's maintained. We've maintained that at 1, or 0 dB. If you look at what happens when S is equal to 0, you have 5 over 5, or a gain of 1. Now, we want more filtering. We want more filtering. We want more filtering. Meaning we want to roll off quicker in the stop band. We want it to have a sharper slope. That means that we can increase the order, and this is what we talked about last time. Here's the warning. Even though you know very well how to create a first order normalized transfer function, 1 over S plus 1, you can't just keep putting those together, cascading those to produce second order, third order. You can, but now we're going to show you why that's maybe not what you want. So creating a second order filter, we're just going to go at stages here. Creating a second order filter by cascading 2 identical first order filters isn't going to work to preserve that cutoff frequency that we wanted. And here's the illustration that I tried to quickly, and I know everybody had turkey mind or something last week, so we're reviewing that. We now have H of S is our normalized low-pass filter, has a cutoff frequency of 1 radian per second, and we can now find what its true magnitude is going to be at the cutoff frequency, at omega equal to 1. We can evaluate its magnitude, its absolute magnitude, which is the magnitude of h of s with s replaced with j omega and evaluated at omega equal 1. We're simply walking up the imaginary axis. We have a pole at s equal to minus 1, and we're trying to find what's the length of that hypotenuse, and that's what's giving us our length in the denominator. The numerator is of length 1. What I just tried to describe, which I was getting some looks of, I'm not sure what he's talking about. So let me try to make a sketch. Here's the S-plane. You have a pole at minus 1. We now want to know what's the value of the magnitude, and when we're looking at the frequency response, we're evaluating this transfer function along the imaginary axis. That's what I've shaded in yellow. And at the cutoff frequency, which is right here at J1, the pole will give us a magnitude equal to that distance or that hypotenuse that I've dashed in that S-plane drawing. The numerator, so this is now giving me the length of j omega plus 1 when j omega is actually 1. And you can see that if you start at the pole and you walk over 1, there's the 1, and then you take a hard right or a 90-degree turn and you go vertical J1, that's now where you're going to from where you were. That gives us this length, and that length is what's right there. That's the length of the pole factor. The numerator was just a 1. It didn't have any zeros, finite zeros involved. We take the magnitude of 1 plus j1, which is now 1 squared plus 1 squared, or that gives us 2. We now end up with an actual value for the absolute gain at the break frequency of 1 over the square root of 2, or 0.707. We're 70% of where we were if we put in, let's say, a sine wave of amplitude 1. We're now at 0.707 at the output if we had a frequency of that sine wave of 1 radian per second. We could also express that in dB. Did anybody have any Black Friday luck with their protractor or straight edge or slide rule? No? I actually looked for a circular and didn't see any, so. And I looked for emails. I was attentive. I looked to see if anybody emailed me an ad that I have to get up at 2 a.m. to go get this protractor for 5 cents instead of 6 cents. Save a penny. Lose 4 hours of sleep, but I get a penny savings. You're engineers. You can do better than that, right? Where are we? Oh, still trying to figure out. Without a calculator, you've now created over that holiday break, you've done log of 1, log of 2, log of 3, and you made your table, right? Yep. They tolerate me. That's fine. So now we have a minus 3 dB decrease in magnitude at the cutoff with a first order low pass normalized filter. What happens now if we just by sort of saying, well, that's a first order, I want more filtering. Let me create a second order by just cascading 2 of those transfer functions together. Now I have a 1 over s plus 1 and another 1 over s plus 1. Let me see how that works for me. I now have a 1 over s plus 1 quantity squared. This is to give me what? More filtering. I wanted more filtering. And this will do it. This will give you how much roll-off in the stop band. What's the slope? It's now second order, so you now double the minus 20. It's now minus 40 dB per decade. So we do have the steepness in the stop band that we want in terms of our slope. What we want to do is check, are we maintaining the 3 dB frequency at omega equal to 1? And this is what we talked about last time. No, it actually goes away. So let's just do the analysis and convince ourselves of that no answer. We do exactly the same process. We replace omega with omega equal to 1. But now we're squaring that original 1 over j omega plus 1. Because we've now doubled our filter order. We have a second order filter. Downstairs, we're still looking at 1 plus j1, but now we're squaring that because we have two of them. We now have two poles sitting at, in this h tri, we now have two poles right there at minus 1 in our complex S-plane. And when we get up to J1, we not only have one path up to that frequency, we also have a second length from that second pole. So they both are giving us additional gain. That's why we have that 40 dB per decade roll-off in the stop band. But now, when we square the denominator, we're essentially getting rid of the radical, and we have 1 over 2, 1/2. Instead of being at 0.707 or 70% of where we were, now we're at half. So this is quite a bit lower in terms of attenuation at our desired location of omega equal to 1. We no longer have maintained our cutoff frequency at omega equal to 1. In fact, at omega equal to 1, we had a gain, an absolute gain of 1/2. We take 20 log of that, and we can now go through the algebra, and now we multiply the 0.3 by 20 instead of 10. So now we're down not 3 dB, but 6 dB at omega equal to 1. And that's illustrated, it's illustrated right here in figure 15.16. It should be very clear. Let's see if I can find it. Here's the figure 1516 for cascaded first order filters. This is not Butterworth. This is if you simply said, you know what, I really like that 1 over s plus 1. Let me just keep packing those together. You pack a second one in. That'll give you the second order line. You pack another one. That gives you the third order line. And do you see what happens to the magnitude? The yellow highlight is in fact what's our normalized frequency of 1. When we have the first order, we're hitting the minus 3 dB just right, just as we had thought. But then when we look at the second order, which is this next curve, where are we? Well, we just calculated that's minus 6 dB. So we're rolling off before 1 much sooner with the second order than we were with the first order. And so if we went back and said, oh, what is my actual 3 dB frequency? Now do you see that it's 60% of what it was before? we're now at 0.6 instead of at 1, with just cascading two of those first order factors of 1 over s plus 1. And it gets progressively lower and lower in frequency as we increase the filter order from third order to fourth order. The third order, you can follow that back and say, where does it now cross the minus 3 dB line? And now we're down to half of what we wanted. So we've destroyed our design. If somebody says, well, wait a minute, I thought I should be passing a frequency of 1 radian per second. And you go, well, it's really attenuated. What'd you do for a filter? I just put a bunch of first order normalized stages together. Now you can go and look at figure 1516 and say, that's not going to work. I need to do something different. So what we want is we want H at J1. 1 is our normalized cutoff frequency. We want to maintain that at 0.707, or the 1 over the square root of 2, for all filter orders, for n equal 1, for n equal 2. We don't want this behavior that we're seeing in 1516. And that now says, oh, we need to have a different pole pattern. Now we need Butterworth pole pattern to maintain that flatness in our... So what we're trying to do is, no matter what the order is, what we're trying to do is say, oh, you want a second order filter? You now want it to go here, but then roll off. So that should have been parallel to that one in terms of its slope. That was pretty ugly, so I'll erase it. But do you get the idea? You now want to be flat as long as you can until omega equal to 1, and then you start rolling off. Here's the polynomials, and you should have this also. Maybe you can do it on your calculator. These are the Butterworth pole locations. These are the factors that you would place in your denominator of a normalized low-pass filter if you wanted that filter to be of order n. If you want a first order, it's what we expected, s plus 1. Otherwise, for a second order, it's not this. It's not that, is it? Now we've replaced this with something more appropriate. And the appropriateness is now square root of 2. And if you look at the roots of this, if you now plug that into your calculator, boy, good thing we have a calculator, huh? So now you could use the quadratic formula and find the roots of that. How far are they from the origin? How far are those roots of n equal 2 from the origin? Can you tell by inspection of that polynomial? What's the natural frequency? What's the distance of those two poles? If you now said, oh, I now have these poles and they're somewhere over here. Where are they? I'm asking, how far away are they from the origin? That's our natural frequency squared. They are always 1 away, no matter where they are in this order, they are 1 away from the origin. we now need to figure out where are they on that radial distance of 1 from the origin. How do we find that? If we don't have this chart in front of us, how do we start creating Butterworth pole patterns that we can now use in our filter design? If you found the magnitude from each of those, if you plugged all of those denominators for the various powers of n into the denominator and then took the magnitude, you could show that it looks like 1 over the square root of 1 plus omega over omega c, where omega c in this case up above is 1 raised to the 2n. So that's the magnitude of our Butterworth low-pass filters for any order n. Here's what that does, or how that translates into their locations in the complex S-plane. We build up another table. We say, okay, the filter order is little n. The angular separation of all of our poles is determined by little n. We now are on the entire complex S-plane. You give me an n. I double it, and then I divide that into 360, and I say, oh, that's the angular separation between all of the poles, and now I'm going to have twice as many poles as I need. I'm going to throw half of them away. The half I'm throwing away are in the right half plane. I don't want unstable poles in my filter. Here's what we do. With n equal to 1, we use that formula and we say, oh, you now have 2 total poles, of which we're just going to retain half of those. So we're just going to retain 1 of those. And those 2 poles are going to be separated in their angular separation by 360 divided by 2 times n, or 180 degrees. That then says, okay, where do I put those? Well, they have to be symmetric with respect to the origin. And we know that for a first order, we're going to have one of those poles at -1. The other one's at 1. We neglect that. We now build our transfer function from that blue pole. That's what's in the denominator, and that corresponds to this factor in the denominator. What if we now up that to a second order? Now we have 4 poles. We divide 360 by 4. That says that our poles are separated by 90 degrees. Do you see that this is the only orientation of 4 poles separated by 90 degrees that's symmetric with respect to the origin and preserves 2 in the left, 2 in the right? If you rotate it at 45 degrees, you could have 2 on the imaginary axis, and that kind of doesn't work, does it? They would all be separated by 90 degrees, but then we would only have 1 pole in the left half plane, and we wanted a second order filter. We now know that we need to have 4 poles. We'll discard 2, but those 4 are separated by 90 degrees. How do we rotate those? Well, we rotate those in such a way that we have half of them in the right, half in the left, and they're symmetric relative to the origin. Which means, oh, and how far away from the origin are they? All 4 of those are 1 away from the origin. We now know by symmetry then that we could compute the real component and the imaginary component of those 2 poles that are in the denominator. And you could have found those also by simply plugging this expression into the quadratic formula. Here you could say, oh, the real part of that pole is 1 times the cosine of 45 degrees. And what's that going to give you? Root 2 over 2 is one way of calling it. What's the imaginary component? Same distance, isn't it? Because you have a 45-degree angle. This now is at minus square root of 2 over 2 plus j square root of 2 over 2. And you could determine that simply by knowing, oh, I want a second order. That means I take 360 and divide it by 4. I know I have 90 degrees between all of my poles. I need to rotate those so that they're symmetric with respect to the origin, and I have 2 in the left and 2 in the right, and I neglect the ones in the right. Now I know what they look like or where they are located. I can now compute because I know this distance, this natural frequency, is 1. This one, same distance into the left half plane. It's just now minus j square root of 2 over 2. What if we did that another factor larger? Now we have a third order. Now we divide 360 by 6. Now our poles are separated by 60 degrees. When we have an odd number of poles, we're always going to have one at s equal to minus 1. And now you can say, oh, but I know my poles are separated by 60 degrees. The other one's 60 degrees above me. The other one's 60 degrees below me. And I can compute where they are by trig if I want. And that will then correspond to, if you now, the table that was provided is factoring out that factor, but the quadratic factor now will give you those two roots that are 60 degrees away from the real line. Now, can you draw the picture for 4? Yes, you can. What would it look like? It's now even. Do you have any pole on the real line? No. So now you have to, and how far apart are these poles? 360 divided by 8. So 360 divided by 4 is 90. Let's divide that again. It's 45. So now we know that 360 divided by 8 is 45 degrees. And we know that we can't be on the real line, so that 45 degrees is going to be split, bisected by the real line. That means now that first one is 22.5 degrees above the real line. The other one is minus 22.5 below. The one above, the first one above the real line is 45 degrees beyond it. This is now the picture for n equal 4. And you could compute with some trig their exact locations, or you could factor those two polynomials that are provided right here. Here's one, and here's the other. And the roots of those two, so you just have to be able to do the quadratic formula from this table if you wanted to calculate your roots that way. Or if you liked trig and you liked drawing, you could draw this and say, here's my constellation of pole patterns for a Butterworth filter. Why are we doing this Butterworth filter? I forgot. So I can have an nth order. What's special about these pole locations? Ooh. My foot cramped, sorry. So if I go down, you can leave. I'll just try to pull my toe back. Where was I before that happened? Help me. Where was I? What's special about these locations? Why are we interested in a Butterworth pole pattern? Pardon? The break frequency is maintained at omega equal to 1. And their Butterworth, did anybody do some shopping? They produce a maximally flat magnitude response in the passband. They go really, really flat until they get to that break frequency, and then they bend, and then they start zipping down depending on how large or what n is, what little n is. N times minus 20 dB per decade gives you the roll-off amount. The Butterworth gives us that nice flat magnitude response in the passband, and then we have that sharp cutoff or roll-off. See? We did some shopping. We were in the syrup aisle, and we found Mrs. Butterworth. And now we could say, you're low on your syrup. But now you have this maximally flat response based on these pole patterns. And what I'm hoping, if you take anything away from this time together, is, oh, now I sort of understand where these poles are coming from or why they are located where they are. You can fill in that table. You can say, oh, they have to be the same angles apart, and if I have an odd number, where do you know you're going to have one of those poles? Always at s equal minus 1. The others are going to be away from that by the angle determined by 360 divided by 2n. So here's the strategy for building normalized Butterworth low-pass filters. If you want n equal to 1, you use figure 15.1, which is what we started today with. That active low-pass filter, that first order stage. If you want n equal 2, then you go to the second order filter stage, which is right here. You now build your filter with this. And once you have this, can you derive the transfer function for this filter? You should be able to. Once it's derived, you now have it in terms of the R's and the C's. The R's are exactly the same. Now you're going to have a denominator that contains R's and C's. You now know how to pick those R's and C's based on your coefficients in the table. If I wanted n equal to 2, if I just wanted n equal to 2, what was my polynomial? Wasn't that s squared plus the square root of 2s plus 1? And now you're going to have in these locations parameters containing R's and C's. Now you know what those R's and C's need to be in terms of their values. You find those, and those are now your original R and C values. You say, I don't want a bandwidth of 1 radian per second. I want something else. So you frequency scale. You can find new R's and C's based on our frequency scaling formulas. You say, yes, but Josie just gave me 10 microfarad capacitors. Then you magnitude scale so that your final value of capacitor is 10 microfarad, and you figure out what is my magnitude scaling factor, K sub m. Oh, now I need to scale my resistors to be consistent with those capacitor values. If in fact you now had some higher order filter, let's say it's third, you just put these pieces together. These are just like puzzle pieces, and you really just have two to keep track of. You have one that's first order and the other is second order, and you just keep putting them together. However, in the second order, the values for those R's and C's are going to depend on whatever that second order polynomial is in that scenario. For example, for a third order, this is no longer s squared plus the square root of 2s plus 1. That was what it was for a second order and a second order only. Now we go back to this table. Am I on the right page? Wrong direction. Oh, why did I go back so far? We go to this table and we say, oh, here's how we introduce our first order piece. That's consistent with what we had for n equal to 1. But now if we want that second order factor to have slightly different coefficients, we now want, in our third order case, this one is now s squared plus s plus 1, and this is s plus 1, to obtain the normalized first order filter behavior. Up here, this was s squared plus the square root of 2s plus 1. This one was s plus 1, as we would have expected. Now, when it's n equal 4, we have to throw those two previous quadratics out and get two new ones, because now they are not in the same locations. These four poles don't overlap any of the previous poles. This is now a fourth order Butterworth configuration. We now would go back here and say, oh, for a fourth order, I need one of my second order factors to have these coefficients and the other one to have that one. Or we now come back here and we say, oh, in this particular strategy for building a fourth order filter, I would put one of these at s squared plus 0.765s plus 1, and this one at s squared plus 1.848s plus 1. We following the strategy, and these are coming from table 15.1. What if I now wanted to say, well, I don't know what filter order I need? How do I determine that? Well, somebody might tell you how far they want you to be down at the stop frequency. So let me just show you the picture to begin with. They now have on their paper this diagram, and they say, okay, here's a low-pass filter. I know what my passband frequency is going to be, and they'll tell you what omega sub p is. That's 45 radians per second, for example. But then they say, oh, at 200 radians per second, I now want you to be down by a sub s. A sub s might be minus 30 dB. That's going to determine how big that slope is relative to omega sub p and omega sub s. If we now have that information, we have omega sub p, we have omega sub s, and we have a sub s, where a sub s is this distance down there, that's over here, in dB. Now we can go up here and we can say, oh, I can determine what order of filter I need to satisfy that constraint or that design requirement. You now say, oh, my A sub s was whatever I said it was, minus 30 dB. You plug that in for A sub s. Omega sub s was 200 radians per second. Omega sub p was 45 radians per second. You do all of that with your calculator. We'll allow that, and then you'll get N. What if N is 6.2? Now you have to round up an order to achieve your specification. You would say, oh, I actually need N equals 7. It's going to overachieve what I need, but it's not going to undercut what I need if I picked N equals 6. If somebody comes up with 6.1, you may want to go have a discussion and say, should I use a 6th order filter? Is that close enough, or do I need to use a 7th order filter? Are you now able to design filters? And this approximation, I should maybe say, is better when A sub s is more than minus 10 dB, more negative. So when A sub s is minus 20. Did anybody bring their calculator? Do we want to try a design? Suppose somebody says they want a pass band of 150 hertz. And omega s, the stop band frequency, let's say they are wanting that to be 300 hertz. So in fact, what I'm trying to show is that it doesn't really matter as long as you're consistent with these, because it's just the ratio in the formula. You can use in hertz or radians per second. Now I have to say what A sub s is. Suppose now that A sub s, I want to be down by minus 15 dB by the time I hit 300 hertz. Can somebody pull out their calculator and tell me what N is based on this? Pardon? N is less than 3. Okay, so you're going to need a third order filter. Go ahead and plug it in. So now you have, and how was that determined? But go ahead, plug it in. We have, what was A sub s? A sub s was minus 15. And omega sub s was 300. Omega sub p was, or f sub p was 150. So that's 2. We have the log base 10 of 2. What's that? 0.3. So now we have minus 0.02, or 1/20th, times whatever I said A sub s was. Was that 15? Divided by 0.3. What do you end up with for N? Pardon? 2.5. Because what's the separation in our frequencies? 1 octave. And what do we know is happening relative to an octave? We have minus 6 dB per octave. And we needed to be down by minus 15 dB. Do you see why somebody immediately said, oh, N needs to be 3? N equal to 3 says that you now have N times, you have minus 6 dB per octave times N. So if N is equal to 3, this gives you minus 18 dB, and that is enough to satisfy this A sub S specification. So just sort of thinking it through without the formula, you could have justified N equal 3. Now we know that what is our K sub F? What's our frequency scaling? How do we determine that? Wasn't that omega sub 2 over omega 1? Or was it omega, however you remembered it? Was it that? Oh, well, this was 300, and this was 150. Is that right? No. What's omega 1? Omega 1 is our normalized filter's cutoff frequency. So this is our original in our normalized, in this case, in our normalized filter. And what do we want it to be based on this hypothetical discussion? What do we want the new cutoff frequency to be? Do we have enough information? What is omega 2 in this frequency scaling formula? We wanted our passband to be 150 hertz, didn't we? That was right here. That's this frequency. We want that to be our denormalized bandwidth. We want that to be our new bandwidth. We now first, if we started with a normalized filter having a bandwidth of 1 radian per second, we now need to convert 150 hertz to radians per second to give us omega sub p, which in this case is our omega sub 2. So now we want omega sub 2 to be 2 pi times 150. If that's the case, now we know that K sub F is omega sub 2 divided by omega sub 1, or this is now 2 pi times 150 over 1. And where was K sub F last Thursday? 300 pi's? I would have been in heaven. 300 pi, what is that? A little less than 1,000. Is that right? So now we know K sub F is about 1,000. We can now frequency scale our R's and C's, and we now know what is our denominator polynomial. We now know that it's looking like this. We have one pole at -1 and the other pole at the values given by this, which will be minus 1/2 plus and minus j square root of 3 over 2. That's where they are. That's in the normalized case. We scale that up. We expand that unit circle to a circle of about 1,000 because that was our case of f. That's how far they are now into the left half plane. And we know that they are staying at the same angles orientation-wise as these normalized cases. Questions now on filter design. If you have them, let me know, but I think we're maybe getting a feel for filter design.